So what we want to talk about today is kind of getting into databases and database design. I've got kind of an overarching agenda on the board about what we're trying to get into today. We're going to review a little bit on the history. We're going to talk a little bit about theory and ERD diagrams, UML diagrams, how that fits in as well, just another way to do the modeling. Then we're going to do a group exercise where I'm going to have you all make a UML diagram as pairs of two. So that's part of the plan today. That group exercise is for lab credit. You'll be turning it in on Inside Ranken. It's just a file upload. And what I need from that is it'll be a UXF file is what I'm looking for. Okay? So that's kind of where that's going. Last thing we want to do today, then after that, is we want to go ahead and get MySQL installed. There's two things that you'll need, namely MySQL Community Server and MySQL Workbench, and we'll kind of look at where to get those and where to install those. So that's kind of the plan for today. Tomorrow, we're just talking about databases in theory today. We'll be talking about databases in concrete, specifically MySQL tomorrow. So that's kind of the agenda. Cool? Questions? Okay. So talking about the theory a little bit. One of the questions I asked is, how long have these databases been around, right? And that's a good thing to kind of understand. And if we think about databases as a store of knowledge, right, we've needed to store knowledge and data for a lot of reasons going back many thousands of years, right? So if you think about them as a store of knowledge, yeah, you can say things like books and libraries or ancient hieroglyphs in Egypt. Yeah, those would be considered a way to store data. Not in a digital form, obviously, and that has some limitations. But they're things that we used to use. In fact, in some ways, the old card catalogs that you used to see in libraries are kind of the way that they used to manage and know where books are. That has a lot in common with how indexes work in any database system that you use. So we kind of borrowed that idea of a card catalog and called it an index, and we use that with every database that we make. Okay, so that's one of those things that kind of falls over. As far as kind of the origins of electronic databases, yeah, we're really talking about late 60s, early 70s is when we first saw electronic versions of these rather than physical paper versions of databases. Okay, so they actually date back, if you notice what other things coming about around the 70s, basically date back to the beginning of computers. It's one of the very first things, in fact, that we needed to kind of come up with, right? First thing that business wants to do, well, they want to track orders, they want to track shipments, they want to track what do they have in their inventory, and, well, spreadsheets can do some of that, databases do it better. And so that's where those really fit in. Okay, so it's important to understand this really a core business tool that we've been using basically as long as we've been using computers in business applications. Make sense? It also, we'll talk about a little bit about where that fits in with the hardware, because the other thing that's kind of determined is how relational databases, specifically how they function and how they got to be as popular as they have been, is partly out of that environment. And so not everybody knows the history, so that not everybody knows why certain decisions were made and why they function the way that they do, or what that means for today. So in general, one question to start with is, why do you need a database, right? Why does your business need a database? Or why do you need a database for the web applications that we're going to build? Because databases are not the only way to store data. They really are not. I mean, we could easily say, let's store the data in memory, right? Let's just say, hey, we've got arrays and we store them in memory. Well, what happens immediately as the server shuts down? If I just store it all in memory, I lose it all, right? And that's not a workable solution for most applications. In fact, if I need to have, the other thing that happens, if I need to spin up multiple servers because I've got a bunch of load, let's say I need a server here and a server in China and a server in India, Well, those don't share the same physical hardware. They don't share the memory. So I've got data here that's only in the US and data here that's only in India and data here that's only in China, right? I need a way to have that data be shared globally is another one of those common requirements. And so databases fill both of those needs. That's part of what they're there for, is keeping the data long term, is keeping it beyond just the server reboot, as well as keeping it, making it globally available. Those are some things that we really need out of our databases today. Now, that's not universally true. So for instance, there's a database out there called Redis, which is a really, really popular database, but it actually loses all of its data when you reboot the machine. And that's intentional. It keeps all the data in memory. Because what it's very good at is doing something called caching, where you say, okay, it takes a lot of work to create this page, so we'll just save it temporarily in this Redis database, sometimes known as a Redis cache, so that we don't have to regenerate that data every time. So Redis is kind of an exception to that rule where actually we don't persist the data. We don't want to because we're trying to do a cache instead. But most databases, in general, that's one of the things we're trying to get out of it, right? So what are some other alternatives that I can use to kind of fill that same need of saving data past a reboot, past a server reboot? What else could I have used? If we're talking about the hardware, right, where does data stick around if you reboot the machine? Well, in the disk drive or an SSD, right? We call it generically, we call it permanent storage, okay? So we say as long as I put something in permanent storage, it will be there when the machine reboots, right? And so as long as it's on if it's on a magnetic disk drive, if it's on an SSD, those both things, if you shut off the power and turn it back on, the data's there, okay? We also historically have also used old tape drives. Literally, this is one way that databases were stored historically. You talk about the 70s, that was really common, that your whole database might be on this giant tape and like the roll was that big kind of thing. You think if you've seen a VHS tape, it was that big, but the rolls were this big. It's like that.
So it would be super crucial to have like data backed up with another source.
Yes, those tape drives are very easy to break because if you've used VHS tapes, you know how easy it is for things to get jammed and whatnot. Weird thing is, historically, they were actually used as backups. They have been long used actually as a backup mechanism, which I think people are finally coming around to that being a bad idea.
I thought that was because they have such good longevity.
That's kind of the theory, but they're very easy to damage, right? If they're undisturbed, they have decent longevity. But if you disturb them, if you're actively using them, if they're using them to say back a website, that's not going to be the case because it's going back and forth all the time. Chances it's going to jam and break. So it only really serves that function if you use it rarely, right? So the one case where that's used is where you have things like maybe a monthly or quarterly backup. That's where it might go to a tape drive, right? But other than that, they've basically fallen out of use. But it is one thing that exists there, right? So as long as it goes to that medium, we have persistent storage, right? As long as it goes to any of those hardware mediums that survive that, that's good. Now, we run into some problems in that, yes, for the most part, if you shut the power down, you keep all the data, okay? Except for oftentimes the most recent data that you've written or the most recent data you're in the process of writing. Because actually writing to the physical media, saving that data is much more complex and actually takes a good amount of time. So there is some processes, some hardware and some software that makes it look like it's faster than it actually is. So what we oftentimes do is when we say we want to write data to a file or something like that, first Windows kind of takes that, puts it into something we call a buffer, and kind of saves it actually in the computer's memory. And then later, as it has time, it will read and work from that buffer, get it onto the physical disk, right? And if it's just in that buffer, if you shut the power off at that point, you've lost the data, okay? But once it gets through the buffer, then you're good, except for not only is there a buffer on Windows, there's also a buffer in the hardware. So when you write to the actual drive, when you actually write to the hardware, it puts it in this buffer temporarily until it has time to actually write it to the disk. Okay, this is especially an issue with SSDs and flash drives because there's a limited number of writes that you can make to every sector, every cell on the SSD before it's completely inoperable. So to reduce the amount of physical writes that happen, we do a lot of buffering. Okay, so we do a lot of buffering, and that means, in fact, we had one case where one of the things that we did is we had these mobile phones, these Android phones, and we would have them back up data onto a flash drive so we could then transfer it over. And it turned out that depending on the cable and the flash drive that we used, sometimes it was just a matter of seconds for that process to complete. Sometimes it took up to 30 minutes for when the Android Linux said it's written to when it was actually there on the hardware, actually there on the flash drive. You know, you kind of think about in Windows, is everybody familiar with like the safe eject sort of thing? That's why that exists. That safe eject says, force everything to be written, make sure it's saved before I go pull the thing out. So if you don't safe eject, anything that's in the hardware buffers or your Windows buffers might not be there. I had a case in one of the my networking course where we finished the entire lab project, pulled the flash drive out, and found out afterward that there were no files on it because we didn't eject it. So we had to do the whole lab assignment again. So it can be a lot longer than you might expect for those files to be written. So that's one issue that you run into is how do you deal with that? How do you avoid losing data given that buffering is at play, both in the hardware and the software? Does that make sense? So if you're writing directly to files, if you're working with files directly, you as a developer have to deal with all of those problems. You have to deal with making sure that it gets written, making sure that time delays are in there, to make sure all of those things happen. And that becomes an issue, right? In fact, it takes some really smart people to get that right. So one of the things that one of the things that databases do as well is they help manage that process for us. They help manage that process of making sure data isn't just kind of lost when we shut down the computer because of things being in buffers, right? So there's a lot of fancy logic that deals with that, including something called a journal. Databases, you know, really all modern databases have something called a journal file, which tracks every change you've told it to apply to the database. And so it can kind of save it to the journal before it actually does it. And that way, if something goes wrong with the hardware shutting down, it can try to go back to the journal and fix corruption issues that might have happened with your database. So that means that if something does go wrong, more than likely that journal is able to kind of play it back and either go back and forward in time a little bit to get it to where all your data, none of your data is lost, or at least only a little bit of it is lost. The flip side with saving things to files directly, let's say I'm saving it to a file directly and I'm saving it as JSON. Well, JSON starts with a curly brace, right? And then I might have a key here. Maybe this is my password. And the value is secret. Okay? So let's say I'm saving this to a file. So this is a JSON sort of point. It's got an object, you can see with the curly braces, and it's got a key and value. Okay, so as long as I save the whole file, everything's good. If I lose that one character, I can't load the file anymore. If that last curly brace doesn't get written, you can't read the file. basically any JSON parser that you've got. See the problem? I lose that one last character, I've lost all of the data. You see that being a problem? So you can try to do some of this yourself, but then you have to watch out for things like that. Same thing happened when you're dealing with XML. Prior to doing this stuff with JSON, we would used to write things in XML to files, slightly different format. So I might say config, and I might say password as a tag. Looks very similar to HTML, right? It's got opening tags and ending tags. This is XML though, because XML lets me create whatever tags I want, okay? Versus HTML, you have to use the predefined tags that's there. So the idea being that the XML is for data and HTML is for rendering pages, rendering documents. Well, it has the same problem. If I lose any of these characters from the closing tag, I've lost the whole file. Does that make sense? Because it's only valid as long as every tag is closed. So if there's any error anywhere in there, then something goes wrong. In fact, it could be something as simple as that's data you have now lost because I can't read that data because there's no closing tag for password. See the problem? So we really want to avoid reading and writing files ourselves, at least in the context where that data is being changed in the application itself. It's one thing, like we're using configuration files, whether it be XML or JSON is really common, but you kind of have this assurance that they're not changing by the application. They're basically fixed. And so then we kind of say, okay. Does that make sense? So it's part of where databases fit in, is managing all of that and managing the hardware to make sure that it's used effectively and that we don't lose data. That's part of the job of the database, okay? And so one of the things that helps is it does remove you a step away from the hardware, right? So you've got your database management system. This is a software you're talking to. It's talking to the file system and Windows and the operating system and the hardware for you. So you don't have to deal with any of those APIs. Make sense? So that's part of where that fits in. So I honestly don't write a lot of applications anymore that deal directly with files because I usually find that it's better in most cases to put that data in the database. That there are exceptions to that rule. For instance, if we're talking about any media, if we're talking about audio files or video files or pictures, those are still better as files. So better to use those in the file system. We don't put those in the database because it doesn't handle binary data like that well. But it's very good for other things. Another kind of common thing that the database is good at is it really helps handling multiple users that are multiple concurrent users. So that means, let's say, hey, you have this system and it needs to be able to support 100 users connected to it at the same time. Well, working with files directly is not going to be efficient for that. In fact, you're more than likely going to end up with a corrupted file if you try to write the files and manage that yourself. But databases have a lot of security in there, a lot of tolerance to try and handle that, to try and handle the concurrency that's necessary for modern applications. Okay, so that's one of the places that they fit in, is trying to handle that concurrency as well. Another thing that happens here, one of the things that we compare, when you're starting a new business, if you say, talk to small business owners, a lot of times they will start by having their data in spreadsheets, right? That's how business people are kind of familiar with with working with data and sales figures is they'll start by creating an Excel spreadsheet to manage all their expenses and all their finances and all those kind of things. Well, what happens if you've got two people that need to update an Excel spreadsheet? How do you manage that? How do you make that happen? Traditionally what? Well, there is a way, and I see people do it all the time still.
I'd say like cloud, an access group of that group.
Okay, that helps, right? And people are using cloud because of that. Cloud is one part of that. But even people who are using cloud usually end up into something else as well. Okay, so here's what happened, especially before cloud services were an option. What would happen is I would say, okay, I've got the spreadsheet of all the products that we've got in our store. I'm going to send that out as an email so everybody on the company has a copy of the current products we sell. Okay, so somebody else makes a change. When they make a change, they email everybody the updated spreadsheet. And the next person comes along, takes that updated spreadsheet, makes a change, emails everybody. Takes a change, emails everybody. Inevitably, something happens where somebody's using an old copy of the spreadsheet and makes a change to that and emails it out to everybody, and now there's two floating out and one of them's wrong. What were you going to say, Don?
That sounds inefficient.
It is very inefficient, but a lot of companies still do that, right? A lot of companies still do that. And so what companies that are smart have done is they said, well, at least we'll take that spreadsheet and rather than emailing it around, we'll say, well, the only place that that's kept is on some sort of cloud service, whether it be Dropbox, whether it be Google Drive, whether it be OneDrive, any of those three. You put the file up there and then you say, well, the latest version's there. Anytime you want to make a change, you make it there. You still have the problem that sometimes people are trying to edit the same file at once. And so OneDrive and Dropbox and those things are not perfect. And so you can still lose data if two people try to edit it at once. Cool? So that's kind of what happens, and that's still happens. I would think at this point that most businesses have learned the lesson that that's a bad thing to do, but marketing from Dropbox and other companies is still pretty high, right? OneDrive is pretty pushy on Microsoft is pretty pushy about installing OneDrive on every Windows 10 machine. And say, like, well, every business should use this. This is where you should keep your files. But you run into problems anytime you have even just two people potentially editing that file, right? So you basically run into this boat where the safest thing you can do is say that there's only one person in the company who's allowed to edit this file. And they have the one that we call the source of truth. They're the owner of that data. And so any changes to that data have to come through them, problem solved. Except when they go on vacation for 2 weeks. And you can't you can't put any new products on your website or anything like that because Cindy's not here today. So that's an issue, right? So having a database helps us with that problem of it becomes the source of truth, and so any changes to the data go through the database management system. Cool. So that's where that fits in. It's there to make sure in that process of ensuring that there's one copy of it. It means that it's going to help us ensure that the data is accurate. The changes don't get lost because you missed an email or somebody forgot to send you the spreadsheet or whatever else may have occurred. So it helps avoid that, helps avoid some of the data loss. It's also there to try and put some constraints on the data to keep you from having redundant data, right? So I don't want to have two David Jens in the database, right? I don't want to have two Joshes in the database, right? I just want to have one of your customer records. That's it, right? Or I don't want to have the same product on on my store twice, right? If I'm just using a spreadsheet, there's no way to stop that from happening. But if I'm using a database, there are tools, there are mechanisms in there, we call them constraints, to enforce that, to make sure that the data is not invalid. Okay, so that's where they fit in. There's a lot of things that they give us, and basically what that means is 99% of cases, if you need to store data, you probably should put it in a database. Even if you don't know today whether or not you're going to need some of those features, more than likely you will. Unless you can say, this is only going to belong to one person, I'm only going to have one user, you need a database. And have you seen a website that ever has one user? They're not very common, right? Pretty much every website out there needs to handle multiple users connected and using the system at the same time. So you have to plan for that. And so that's where everything we do here, we're really going to focus on putting that data into a database. Okay. Another thing that happens, let's say you're sending a spreadsheet around. And again, I said I'm sending it to the whole company. Who has access to that data now? The whole company, right? The whole company has that data. Okay, if that stuff on my store, maybe not a big issue because everybody can see that, no big deal. What if it's employee records? Do you want everybody to have access to everybody else's employee records? Probably not, right? So you need to limit who has access to that. And so you might say, okay, well, let's limit that to only HR has access to the employees database. Okay, so I can say that. And database does allow me to give those limits. But what happens is hospitals are a little bit more protective, for instance. When we talk about something called PHI, protected health information, you really only should be accessing that information when you're working with that patient in particular, right? It's actually a violation of HIPAA if you have a nurse that's constantly looking at every patient in your database. They should only be looking at the patient that they're working with, whether it be billing or whether it be actually being in the room with them or whatever it may be, doing their charts. They only should have access to that one patient. Does that make sense? So that the rules and the legalities are very restrictive on the data that you should be allowed to see and view. One question was asked, I think, about can you limit with a database, can you limit who has access to the data and who can drop data, who can add data, who can alter data? And those do exist. Most of the relational databases give you constraints about who can write the data, who can read the data on a per table basis, okay? One of the things that they don't have, one of the things that doesn't exist in any database that I've seen in terms of relational world is there's not a restriction on saying I can only see these rows in the table, but not all of the rows, right? So with a relational database, there's none really out there that gives you that level of control where I can say you can only see patient X or patient X, Y, and Z. I have to give you the whole table or none of the table. Does that make sense? There is one out there, Firebase, which is technically a NoSQL database, that does have some of those guards in there. But that's the only one that I've seen where you can put guards on a per record basis. Does that make sense? So that's an important thing you have to pay attention to. So what that usually means is not only is there some security and some permissions that happens on the database side, more often than not, we have to put some more restrictive permissions in our applications. Does that make sense? So there may be some guards on a database, but usually, especially in the medical world, we can't use a database directly because we would be violating HIPAA. So we need some sort of application on the front end and tell everybody to go through that application. Cool. And another thing that we talked about not losing data. If we've got mission critical database data in there, say we're talking about booking flights, or say we're booking flights, or we're dealing with hotel reservations, or we're dealing with stock trades, then it's extra important that you don't lose that data because you've got a significant financial transaction that's involved in that. So you have to know what did they pay for and how did they pay that, and so you can't afford to lose that. So databases come into that play as well. Cool. Okay. So you kind of understand everybody needs a database. It's important to understand why we're doing this, because databases come with a lot of extra complexity. They do come up with a lot of extra complexity on top of dealing with files directly. You know, it's not as easy as read the file, save the file, read the file, save the file. It's not that simple. But so we have to understand why are we doing it in the first place, and why would we select one database over another. Okay, and so that's to kind of give that background. Okay, so that's kind of the why. All right, let's talk about what some of the databases are out there. I've already mentioned some of them, but there's actually a lot of databases on the market. If we think about digital databases going back to the 70s, we are, at this point, we've got 50 years of history with databases, right? And so there's a lot of different databases available out there in the market. And kind of the current thinking is there's a lot of ways to group them and kind of organize and think about how to classify those databases. But they basically fall into two groups right now, two large groups. One is relational databases or SQL databases, and non-relational or NoSQL databases. So in general, you've got things that follow this relational model, which dates back to the early 70s, or you've got a non-relational model, which is a little bit newer of a concept. Okay, you saw some mention in the reading to something called a flat file that's really just working with files itself. You can think of a CSV file or a spreadsheet. You saw hierarchical databases. You saw network databases. Those two don't exist, like hierarchical and networks don't exist in their previous form. They do exist in a new form, and part of the things that there were some issues at the time because of how we had approached them at that point, but we figured out some new ways to kind of deal with those problems. So there's some new things that have replaced that. So in terms of talking about what's out there in terms of relational databases, MySQL, Postgres, Microsoft SQL Server, SQLite, Oracle are all really common examples of that. They're really widely used across the industry. And so, SQL databases are pretty flexible. You can really use them for anything. They may not be the best choice for everything, but you can technically use them for anything, right? They can adapt to whatever you want. But they're not always the right choice, which is why we've got some other options that are not relational that fit certain applications better and do some things differently. Okay. At least in theory, all of these understand SQL, at least in some form. The reality is the individual flavors of SQL that they speak is different. Okay. In fact, it's actually at the point where most of the code, a lot of code, you can write it and run it, say, on MySQL, might not run on Postgres, and vice versa. There's enough nuanced differences that the code doesn't usually run from one flavor of SQL to another flavor of SQL. Okay, and so while SQL is sort of standardized, you do really have to learn the nuances of the database that you're learning, that you're using to be effective. Okay, that's one thing to understand. Okay, so over on the non-relational side, there's a bunch of different kinds of non-relational databases, but I only wanted to mention three. So one of them is what's called a key value store, and Redis is one of these. Redis is the most popular one. In fact, if you look at pretty much any major website right now, it's more than likely using Redis in some way. Redis is never used by itself. That's one of the things to understand. Redis is not used by itself because it's not meant to keep data long term. It's meant to keep data in a way that's fastly accessible. Okay, so let's talk about what is a key value database. So a key value database is kind of a simplified version You can think of it this way. Let's say I have a table, and that one table has a key, and it has a value. And every row in there is a record. That's your whole key value database. You get one table, and that one table only has 2 columns. The key, which generally has to be a string, and the value that can be whatever you want it to be. Does that make sense? I think over the summer we did we did our project with local storage using web storage. Whether you're using any of those APIs, local storage is an example of this. So you remember what we did. There were kind of 2 ways to approach this. I could say, hey, here's bug 1, here's bug 2, here's bug 3, right? And so I just say every record in here is a bug, is one way to do that, and just put all of the data for the bug over here. Another way you can utilize that, and you just say, well, it's one thing, and so I'm just going to have one record, and here's the bugs, and here's all the data. Right, so we thought of it either way. It's a few students took it different ways depending on what kind of the choice is. Cool. So the place that this comes up is where the Redis is generally used. Is we do things like we do things like this. We're going to say, okay, I've got my home page. That's the path to my home page. And over here is the HTML for the home page. So anytime you ask for the home page, I just go here into this Redis cache, this Redis database, pull all the data out. And it's good to go. I don't have to do anything more. Or let's say, hey, you have a profile page, and that's at user Danny. And here's the HTML for that page. So that every time I want to go to Danny's profile page, I don't have to go do a bunch of complicated work to generate that page. Does that make sense? So that's the main thing that we use Redis for. We can use it for other things, but that's the main thing. Cool? So you basically, it's a way to circumvent an actual trip to your regular, whatever your regular database is you put it in front and you say, let's check Redis first. If it's there, we don't need to do anything else. Otherwise, we bypass it. So those are kind of the simplest version of a database. The good news is because they're so simple, they can be really fast. But they can't really give you a lot of querying ability because, well, you've only got the key to go by. So the only way to ask for data is you have to know the key. If you don't know the key, you can't get the data. You can't get it efficiently. So I can either I have to know that key to make it work, okay? Other things that we have is Mongo, which you're going to be talking about, is a document database. And so the way that works is when I'm talking about Mongo uses the term collection, okay? And so a collection is kind of like a table. And so maybe I have the users collection, and within there, every record is some sort of object. So this might represent user 1, user 2, and user 3. Okay, but it's just stored as an object. It can have whatever shape it wants. It's very accepting of different kinds of data. Cool? Does that make sense? So every row is kind of as we would say, unstructured. It doesn't have a structure to it. So that's how a document database works. Is every row, basically you can think, again, collections, you can kind of think of them as tables, they're very similar, but they have objects. And graph database is a whole other story. Okay, graph database is beyond what we're going to talk about here. I'm not honestly very familiar with graph databases, but they are very cool. Okay, graph databases fit in really well when you're trying to build a social media platform. Because what they do is they allow you to very easily deal with connections that are much farther separated. One of the things you run into SQL, we'll talk about joins, but joins are kind of painful and they're costly. And so if I have data that's over here and distantly connected to data over here, it is hard to do queries with that in SQL. But graph databases are really good for that. So what a graph database does is it says every entity, everything that I have in the database, let me say, actually, let me make it a box. So we might say, here's user, let me actually put some names on here. So let's see, going from the left, okay, so let's say Chase has got a profile, and let's say this is Facebook, because this is actually works really well for social media platforms like Facebook. And Parker, and then I've got another node out here for Michael. Right? So each of these people, each of these profiles is what we call a node or vertex in kind of this graph scheme. Okay? But what I can then do is I can say if they're friends, I'll put a line between them. And so maybe I'd create a kind of setup like this, right? And so Parker and Michael are friends, Chase and Michael are friends, Chase and Parker are friends, right? So that line in between is what we would call an edge or a relationship. So basically the way the graph database works is it stores nodes, stores vertices, and edges. And you can kind of think of them as tables. So like there's a nodes table and there's a vertices table. Okay, so that means that these edges are actually things. In fact, you can add attributes to these nodes. You can add attributes to these edges. And so I can say, well, you know, if I need to have this relationship, one of the things that commonly happens is, well, who sent the invite and has it been accepted? So I can store information like that on have both members of it accepted the relationship. Does that make sense? That's really good with that. So then when you start to have things where it goes off and you're dealing with a lot of people, in reality it starts maybe looking a little bit more like that. And so I want to do things like, is this person connected to, you know, where are your mutual friends, right? You see Facebook, if you go to somebody's profile, you see what are their mutual friendships, and this is really good for that. Does that make sense? It's very easy to see connections that you have in common. Okay, because I can just say, hey, I'm looking at Parker's profile. Well, it's just the two people that are connected to, so Chase and Mike. Easy, done. It's the easiest query I can do. It doesn't, now, Neo4j, if I remember right, doesn't use SQL per se, it uses a different sort of language. But that's kind of how it works. Does that make sense? So it is really good for things like that, where you have the relationships are much more important. Does that make sense? Where the relationships are kind of more important than the data in some way. But it doesn't give you, one of the things you don't get in here is you don't really get the idea of tables, right? What you can do is you can put on these nodes, you can put attributes, so I can put like a type attribute and say, we can say the type of this node is user. So what I can do with the graph database is say, well, give me all the user nodes, or give me all the blog post nodes, or the comment nodes, or things like that. So I can filter by type, but that's kind of how that works, right? So you can see there's a lot of different flavors of databases that are out there now today. Does that make sense? And depending on what you're building, one of those things may work better for you. Personally, my opinion is I think Mongo works best for most things. That's not everybody's opinion. But that's my opinion. Is kind of the easiest way to get into most of these things. Okay. Any questions? Different database types? You won't hear too much about these. We'll talk about Mongo in the next week or two. But that's kind of how you categorize those things. Cool? Okay. So let's talk about relational databases, because that's where we're going to start. Because that's the thing that we've really been using heavily for really 50 years. Okay. So we want to talk about this week, we're going to start with relational databases. We're going to talk about that for about a week. And then we'll move on to NoSQL when talking about Mongo. So relational databases date back to 1970, created by this guy, Edgar F. Claude, the original inventor of this idea. And if I remember right, he wrote a paper on this idea. I don't know that he actually wrote the code for one, but he wrote a paper about it as a kind of a conceptual model, and eventually got turned into something real and concrete. So he worked for IBM. IBM's been around for a long time. He modeled the data in terms of what we call tables and foreign keys, right? So you have this idea of a table represents, kind of you can think of it as a table of data, and it's got rows and columns. And then you've got foreign keys, which are links between rows, okay? And so that's how you keep track of relationships, is by using foreign keys, okay? Foreign keys and primary keys are the way of tracking how the data is related from one table to another. These relational databases force a really rigid structure on the data. It's really inflexible in most cases. So it has to follow this structure specifically. So for instance, I might say that I've got let's go back to saying I've got a table called users, okay? And let's say I have a first name column. So let's call it first name. I've got a last name column. And maybe I have a username or an email address. Let's call it an email address. And maybe I want a number, so let's call it age. So let's say this is my table, and maybe I'm going to call this employees instead of users. Right? So that's the name of my table. Each of these I've got columns defined, and so what I'm saying is every record in this table has to have all of those fields potentially, right? Every record has a first name, last name, email, and age. Okay? And so what I can do with the relational database wise, I can say the first name has to be characters, right? I can say it can be characters in any language. I can say characters in English. But I can say that it has to be that. What I have to do in a relational database sense is I have to define what the type of that column is. So I might say, well, this can be characters, okay? And so the first name, obviously, okay, that makes sense, it's characters. Are all first names the same length, or are they variable lengths? Does everybody have the same length of first name? They don't. So I need that to be variable length. Okay, so what I'm going to do is I'm going to say, well, this table, I'm using this one instead because it's dying less. I'm going to say this is a var_char. And unfortunately, as it turns out, if I want to put a string into a database, I have to define the longest length of that string if I'm using var_char, right? So I have to say, well, what's the longest first name that I'm going to allow? Somebody give me a number. You said what? 16. Okay, so I can say there's 16 characters set aside. I can hold up to 16 characters in that column. If somebody ever comes along and wants to sign up and be an employee here, that's got 17 characters in their first name,
Same thing.
yeah, either I don't hire them or I have to put part of their name in and abbreviate it, right? Which probably they don't really care for, okay? But I am forced to do that, right? What about the last name? What's the longest that the last name can be? Huh? Okay, so let's say 20. I'm pretty sure, I'm going to guess that there's somewhere somebody has a name that's longer than that. But I can see that. Okay. All right, so an email is also a string, so I can say varchar there as well. How long can an email be?
Are we just including the username?
Well, I can't, because if you just include the username, I don't know what the domain name is.
Okay, well, it's a matter of perspective, right? They're
Right.
employee, we know what the name is.
Not actually generally true. Generally, you can't make that assumption. Because there are plenty of companies where people are on different domains. In fact, here, our students are on insideranken.org, and I'm on, teachers are on ranken.edu. So even with us, we can't make the assumption that we know the domain. Okay. So generally, the safe assumption is, that's one of the things that I would really strongly suggest avoiding, is assuming that we know the domain name. Okay. In all cases, because usually that ends up being incorrect at some point in time. So how long can an email be?
120.
120? Let's say 120. Is that a hard limit? Could somebody come up with an email that's longer than that?
Yeah.
Certainly.
Okay, certainly, more than likely. If we think about what an email consists of, right? Emails are actually really, really complicated. In fact, there's a lot more that's valid in terms of an email address than you've probably ever seen. And I know that there are things that I'm not aware of that work as an email, because validating email address is really, really hard, because there's things that go in there. Well, if we're talking about an email address, it starts in theory with a username. Okay? Simple version is username, and then an @ sign, and then you might see a domain name. So you might see Ranken.edu, right? That's kind of the simple version of talking about an email address. Okay? Working from the left to right, what characters are valid in the username?
Anything.
Any of them.
Practical.
Okay. Well, what do you mean by any of them?
Probably everyone on the keyboard.
So like symbols, numbers,
Okay. Are all symbols valid? Yeah, it's a subset of symbols, but there are some symbols that are valid.
Probably the ones that are imaged in the keyboard. They're plenty that aren't on the keyboard, right?
Well, yeah, there's some truth to that as well, but not even the ones that are on the keyboard. Because, for instance, what if I have an @ sign in there? Right? That's really a no-go. You can't really have an @ sign doesn't make sense in this first part. Okay. I can have dots, I can have dashes, I can have underscores, I can have a lot of other characters. In fact, if you've got a user that's from Russia, they might even have Russian characters in their username. Right? So you can't even assume that it's English characters. Right? It could be in another language. So that's another thing you have to watch out for. Another thing that I wasn't aware of until a few years ago, you can also put comments, as it turns out, basically into your username.
What did you say?
You can put comments.
Comment?
Comments. It's actually legal to put a comment into your username. There's a syntax for it. I forget what it is, but there is a syntax for putting a comment. I think they call it a scope, basically. So some people use that to say, I'm going to direct all my spam to this other email address, so it just kind of gets lost, or those kind of things. So you can actually put a comment in that username, which means that if somebody can put a comment, then they technically have several email addresses that go to the same place. which gets interesting. Okay, when we talk about the domain name, let's kind of look at the end, edu, that's what we call a top-level domain, a TLD. Okay, if I remember right, ICANN is the company that manages that and set aside what those are. What's the minimum and maximum length of that TLD?
2 and 3.
Huh?
2 and 3.
No. It's not 2 and 3. What are the 2 and 3 are you thinking of? Well, obviously, most of them are 3. What's the 2 that you're thinking of?
.jp, .co, .us.
Yeah, .uk is a pretty common one, and JP is a pretty common one. Yeah. So country codes, right? There's a lot of 2-letter country codes. But why couldn't this be? Why couldn't this just be mysite.1? What if tomorrow, ICANN says .1 is a valid top-level domain? I don't want to have to change my whole database or my whole system because I assume that they have to be at least 2 characters long. Does that make sense? So actually, they could be 1 character long. I don't know that there are any TLDs that are 1 character long, but it's something we have to allow. What's the longest that they can be? I know for a fact there are some 4-level domains, and I believe there's some longer than that.
Yeah, I've seen .tech and .space. So.
Okay, .space, how long is space?
5.
It's 5, right? And that's actually a new one, right?
Yeah.
Recently they've allowed 5-letter names. That's kind of new. It used to be mostly 4. Okay, so one of the common ones with 4 is like .info. I think there's also a .movie as well, right? Or there's .tv or things like that, right? So I can't really assume an upper length to that even, and in fact I would say it's generally a bad idea to assume that there's an upper length there, because you don't know if 20 years from now, right, if there's going to be more domain names that are longer, and you don't want to rewrite your code because of that.
But we can assume that there's at least a minimum, right?
So it can be less than 1.
It can't be less than 4 characters in length the entire email address. A@A.1.
That's a valid email address. It doesn't even have to be a dot. Okay. So what I can use there, the second part, the rule about that second part of the email is it has to take you to a computer. Okay. And so that might be a domain name. It usually is. Okay. But it also could just be your computer name. So this would be to go to a computer called local. I'm sending the email to, that's where my email server is. This presumes, generally speaking, that this is on your network, right? So I wouldn't be able to send this to somebody else in another network. But if you're in an intranet, if you're within a business, you can have emails that go around like that. Or I could even shorten it down if I really want to be. I could just say, hey, there's a computer on the system called C, and that's where my emails go to. That's legal. Okay, so it can be a computer name. It can be a domain name. Are there any other ways to represent a computer? I know you guys are not networking folks, but
IP address.
IP address. Okay, so I could say maybe 192.168.0.1. More than likely, that's going to your home router. Your home router could have an email server on it, and so that would say I'm going to send the email to my home router or whatever, or a machine that's on my network. That's legal. Anything else that comes to mind? how many people here are familiar, just a raise of hand, how many people here are familiar with IP addresses, actually? Okay. So do any of you four know the difference between an IP version 4 and an IP version 6 address? Okay, so this is an IP version 4 address. This is the original spec that we have, and we've had it for years. It turns out we have so many internet-connected devices on the planet right now, and we've had actually for several years now. We have so many devices we can't assign a unique IP version 4 address to them. We have more devices than we have IP addresses.
So is that what you get where it's like instead of 0, 1, it's like 1, 1 or 0, something like that?
Well, these numbers can basically go from 0 to 255. There's a bunch of exceptions. There's a bunch of special numbers that you can't use, but that's kind of their limit. If you have all of that space, there's not enough space. Thanks to smartphones and other smart gadgets that we have now, we're actually out of space, and we have been so for several years. There's a lot of tricks that are happening on the network to keep things working with IP version 4. So there's a lot of things that are happening to make that illusion happen. But we've also a lot of networking hardware is upgraded finally to IP version 6. IP version 6, this one right here, if we're talking about bit size, is 32 bits in size, if I remember right, and IP version 6 uses a 64-bit address. So IP version 6 is much larger, but that is valid in an email address. So like : : 1 is my local computer, known as localhost. That's a valid email address. Because both IP version 4 and IP version 6 addresses are valid in an email address. Does that make sense? So email addresses are really, really hard to pin down as what they're valid. Okay. SQL being, for all its rigidity, unfortunately doesn't really give me a way to say what is a valid email address, because I can say it can be up to X number of characters long, but it's really hard. Most of them don't support giving it a format. We might say a regular expression. Does that make sense? So given all of that, IP version 6 especially is really long. If you get a case where you have an email address that is IP version 6 address, this is a shorthand. The : 1 is a shorthand for writing a bunch of zeros. So this could easily be longer than that, because I could have a username that's 120 characters, and, well, hey, I need another 30 characters for an IP version 6 address. Does that make sense? Okay, so it's actually really hard to set that upper bound, but SQL forces you to set that upper bound. Does that make sense? And again, once you say this, I'm saying nothing can go into this table that is longer than that, period. If I want to put anything longer than 120 characters, I have to change the table to be wider than that, which means basically rebuilding the table. I have to make a copy of the table, copy the data over, and then do some fancy footwork to be able to increase the length of that column. Okay, it's kind of a pain. But it can be done, but it's a pain. Okay, now if I'm talking about age, what's the range of ages that I need to be able to store?
The range, like the number of digits, or the actual number?
The minimum and maximum, right? Can I set a minimum age?
I'd say like 10 minutes.
Okay. And at least if we're talking about American companies, what's the earliest that you can start working?
15.
16, right? So I know that 16 is really the lowest number that I'm going to expect in here for an age. And what was the first bound you said?
I said like 100 probably.
Yeah, except that there are people that are older than 100. So I would
Yeah,
say
that's
maybe
true,
16 to 200, right? And so that's kind of what I know is bound, right? And so I need a number that I need enough space to be able to hold that, okay? Now, what's our normal basis? What's our normal size of our numbers? If we're working with our processors, remember you've probably heard 32-bit processors, 64-bit processors, right? Most of you have 64-bit processors at this point. I think all of you probably do. But if I say in C#, I define an integer, how many bits does that take up? That's not quite. How big is an integer in C#?
Yeah, the options are 8 and 32. So.
8 and 32. Well, at 8, 32, actually your options are a multiple of 8, as it turns out. But 8, 16, 32, and 64. So an integer in C# is 32 bits. Same way with Java. Java and C# have landed on an integer is 32 bits all the time. Okay. Long is 64, short is 16, byte is 8. Got it? Other architecture, other languages like C++ and C, the story is much more complicated than that, and an integer isn't always 32. In fact, or 64, it varies. Okay. But in the space of databases, in most SQL databases, we've got an integer type. That integer type does kind of correlate with what we do in C# and Java. So an integer out of the box is 32 bits. Got it? 32 bits stores basically it stores up to the biggest value you can store is 2 to the 31st minus 1. Okay, that's the biggest number we can store. That's overblown for an age. That's way more than I need, right? I don't need that big of a range. So what's the minimum size that I need to store a number from 16 to 200? Byte, right? Because a byte is from 0 to 255. Specifically, if it's signed, right? Or sorry, unsigned. If it can't be negative, then it's 0 to 255. If it's negative, then it's negative 128 to 127. Okay, but I think I'm okay with that. Even if it was assigned, I'd be okay with saying, well, the upper range is 127 years. I think I'm okay with that. So I might say that here we have a byte. Or in the case of SQL, we call it a tiny int. A tiny int is just byte. Make sense? So as you're defining tables, you have to create this rigid structure. Does that make sense? And then the database enforces that. So if I ever try to violate this, if I try to put data in there that doesn't fit that schema, it's going to reject it and say you can't do that. It's going to say, sorry, I can't put that data in there. It won't fit. Go fix your code. Make sense? So if anything violates that. So part of the reason that we do this, right? The part of the reason that they have these types is it's trying to optimize for the usage of space, right? We want to reduce how much space each record takes up. Does that make sense? Okay, so we want to use less space on the disk because that's where we're storing our data, obviously, right? On a magnetic disk, at least that was the thought at the time, right? And so on those disks, you want to reduce how much space is used. Does that make sense? So like, hey, if I can, maybe I can say last names are only 10 characters long, well, then I can cut down how much space that I need by half for that last name. Never mind the fact that now I have people that I can't put in the database. Does that make sense? So that's part of the optimization is trying to fit that in. I can easily say int here. I could just go ahead and say integer. It'll work fine. But now I'm using 4 bytes instead of 1, right? I'm using 4 times as much data if I put an integer there than I need to. Does that make sense? And so when these were created, hard drives are pretty expensive, right? I think you maybe have seen some of that, right? Do you remember seeing that giant Winchester hard drive in the reading assignment? Huge. I mean, platters. I mean, that thing was ginormous, and it was not cheap. Okay. So let's talk a little bit about what the technology was. We've seen some of this already, but when we're talking about, first relational database, he came up with this in 1969, or was it 1970? Yeah, 1970. 1971, we see the first microprocessor, right? So when he came up with databases, we didn't even have microprocessors yet. Okay.
What's impressive is that nowadays we're one to the gigahertz.
Yes. Yeah. And so we're talking about 740 kilohertz, right, at the time, which was still a big boom from what it was in 1961, when it would have been just 10 years before that. But we are well above that. It only supported up to 4 kilobytes of memory. That's all you got. You've got 4 kilobytes of program memory. And that doesn't even mean that the memory came with it. Like, the memory you had to buy separate from this thing. And, well, it wasn't particularly easy to get 4 kilobytes of memory. That was pretty expensive in itself. So it could support up to that. That doesn't mean necessarily you had that much, because you had to pay for that hardware. And this also says up to 640 bytes of data memory. So you're really, really constrained about what you can store, right? You're probably not going to be able to store any images whatsoever to do that. In fact, there's barely enough space for an operating system. Right? How much space does your Windows operating system take up right now? Yeah, gigabytes, right? Right now, Windows, might well take up, depending on the day, might take anywhere from 4 gigs to 12 gigs of memory, depending on what it decides to do. So you can't barely even fit an operating system on this thing. Okay, so here's what disks looked like in the 70s. See this guy in a white room, nice fancy suit, trying his best to not get even the tiniest speck of dust on that hard drive, because it would not work if you got a speck of dust on it. You'd be losing data. Okay, but this giant thing, what I hear is they sounded like this term sounded like a jet engine when it's ramped up, and then to the point where it would spin so fast and it was so heavy that this could actually go through a cement wall if it got loose and started rolling. Go through a cement wall. Okay, that's what we're talking about here. That's what these relational databases were designed to work with and optimize for. Does that make sense? Kind of a little bit different. Okay, so we have to kind of understand that that's what we're working with. So this is 1979. That's a 250 megabyte hard drive, that giant thing. 250 megabytes, okay? Nowhere near your terabyte drive, right? So, and that weighed 550 pounds, cost tens of thousands of dollars, right? It's a very expensive purchase. You can't afford to damage that equipment.
So is that before or after inflation adjustment?
I don't actually know. I don't actually know about that.
So was that powered by electricity, or did it have a motor that made it spin?
Yeah, there is a motor in there to make it spin. Yes, for sure. Yeah, it's a very heavy thing to spin. So yeah, you would need a motor. It would be an electric motor, not a gas motor, but it would be a motor.
Can you imagine that?
It's still an electric motor, and you need that to be fine-tuned enough so you can go forwards and back and those kind of things. So it would be an electric motor, but it wouldn't be a I think, Dawn, I'm going to guess tens of thousands of dollars. I'm going to guess that's without inflation, is my guess. I don't know that for sure, but I'm going to say that's probably without inflation. I think that's $1979 is my guess, which is quite a bit more. So that might actually be closer to, that may end up being closer to $200,000 or something, somewhere in there. It's a very expensive piece of equipment. And so your company, if you were lucky, we have one of these for your company. You probably didn't have two unless you were a really, really big company. Does that make sense? In fact, I think the numbers were, the amount of these that were made is a few thousands of those were made. I think, if I remember right, the numbers. Okay? Versus we look at what we've got here. This is 2013, a few years ago, 16 gigabytes on a tiny, tiny, tiny little piece of plastic like this. And if it gets damaged, no big deal. You can buy a new one. Right? Because it's so cheap. Right? This one's, we're talking about 4/10 of a gram, or 4/10 of a gram, and costs about $11. That for $11, right? Way different, right?
These are even cheaper now in 2021.
Yeah, they're going to be even cheaper than that. They've gone up a little bit because thanks 2020, you know, but that is a whole lot cheaper, right? So it's very easy to buy more of these or replace them if something happens, right? That was not the case here, right? That was not the case here. If this got busted, if something happened to it, somebody threw a hammer at it, you might have lost your entire company's data, your entire orders for the past month.
A hammer?
I mean, come on.
I'm going to have to look at the article to see if that actually happened.
I don't know if that actually happened, but just saying, there's a lot of things that could make this go wrong. Even just, I think the one case that I did hear is that somebody had these got bearings in them to keep it rolling, just like some of the other devices we have, like your air conditioning unit. Well, those bearings can wear down, and they've got to have lubricant on them. If they start wearing down, well, then you potentially have this thing making a very loud noise and getting very hot, right? So there's a lot of things that can go wrong. Okay, does that make sense? Kind of understanding context, right? So the goal of a relational database was to make this hardware be as efficient as possible. Does that make sense? The goal of our relational databases was to make this hardware the best usage that we could get out of it, given the amount of money that it took. In fact, the most expensive thing here, this is actually more expensive than the salary. You know, you're talking about the hardware here is more expensive than the salary of the people who are working with it. Does that make sense? So exactly. So that's worth a few of your employees' yearly salary for just one of those, right? It's the reverse today, right? The hardware is really cheap, right? Yeah, computer hardware. Yeah, that's true as well. But when we're talking about our hard drives, right? Our hard drives are very cheap, relatively speaking. Server hard drives, the hard drives that we use for databases are still more expensive than the off-the-shelf things you find and put in your personal computer. But it's kind of trivial in terms of the cost, right? If you want to say, oh, well, we ran out of data in our database. Oh, we'll just go to Amazon and buy another hard drive and put it in, and we have more data. No big deal. Versus the most expensive thing right now is developers, right? Software developers are the most costly part of writing software right now. It's not the hardware anymore. It's the actual people. Does that make sense? So that's, you know, one of the things you have to understand is that, you know, our thinking has changed a little bit too. Okay, so this relational database was designed to optimize this very expensive hardware, to make it run as efficiently as possible, to ensure that there's no time where it's just sitting there idle doing nothing, right? It should be doing something all the time, and it should be doing something with as little memory as it can use, little memory as possible, as well, because we don't have very much of it. And it has to be using as little space on that disk as possible, because otherwise I won't be able to fit all the orders on there, all of the data that I need to fit, all my inventory. Does that make sense? So we really, really had to focus on optimizing that. And so because of that, these databases are really designed to be hard to change. You're not expecting the change should be frequent. You're expecting that change happens maybe once every 5 years, if at all. You kind of say, hey, we're going to design the database, and then we're not going to touch it. We're going to say, here is the size of those columns, and that's it. If you change your mind and we decide this was a bad idea, we'll end up creating a new database on a new piece of hardware, because that's the scope of that type of change. Does that make sense? So these were designed to be ingrained in things that didn't change. That's kind of where the world comes out of. It's not supposed to be something that adapts from week to week to week based on the changes and the whims of your boss. Does that make sense? I also say in here that it's not designed to be easy to use. Okay, I think there was a question on there. It's like, well, this seems like it's very easy to use. It's easier to use than what came before it, right? Before relational databases, when we're talking about hierarchical and these other flat files and such, in order to use it at all, you had to be an expert software developer. Like, you weren't going to be able to use the database prior to SQL without being a programmer yourself. And programmers were very rare. So you might have a company in the 70s, you might have a company of 100 people, 100 employees. 5 people were the only people that could touch that database, do anything with it. Because you had to be so skilled and so trusted that, like, you were in a state of respect if you had access to the database at all. Does that make sense? Right? You had to have a lot of trust in you that you were going to screw up their whole business just by doing something bad with the database. Right? Does that make sense? Making it do something very efficient, costing a lot of money. Okay? So they weren't designed to be the most user-friendly. They were designed to only really be used by experts. Does that make sense? They're better than what came before, but still designed to be used by an expert, right? And so oftentimes you hear this role called DBA, Database Administrator. That's somebody who specifically, their key job is to manage the database. They're an expert on the database and nothing else, because your database is that important. Does that make sense? And so they're the key, historically they were your DBA was the only person that could make changes to the table structure. You could say, okay, we need to add another table or add a column or modify a column. That should strictly be the DBA, and the developers, they need to fill out some fancy paperwork explaining why we need this change and etc. and get the business to sign off it, and then the DBA would finally make the change. Does that make sense? It's not really the world today. In fact, a lot of companies don't have a database administrator. Most companies today don't have a database administrator on staff. Some of them do. The last company I worked at, we had one database administrator for the entire company. And we were managing up well above 20 different databases that he was managing. He had a very little involvement with our specific team because of that. Does that make sense? So we're at a completely different place. I hope that's one of the things you need to understand. Is there's a lot of things that have shifted, and there's a lot of things you kind of need to understand why they are there. Okay, and so given this setup, these databases actually, yeah, they were designed to deal with concurrent users, but by concurrent users, I mean 5 people. I mean, your 5 employees that have access to this database. They could use it at the same time. Does that make sense? They weren't designed initially to have a lot of different concurrent users. Make sense?
What prevents them from not being able to handle that?
Well, that's a story for next week. But the point is that they were not initially, the initial designs didn't actually call for that. Called for a little bit of concurrency, right? Better than having an Excel document that everybody's passing around an email, but not designed in a way where 100 people can get on there and use it at the same time, right? The hardware is too expensive to make that make sense. Okay, so you're really talking initially, you're talking about 5 people being on there concurrently and trying to do jobs, and more than likely, those 5 people might have to wait turns to run their jobs. Okay, and they would kind of plan with each other, make schedules about, I'm going to run this at this time, and this at this time, and this at this time, because it took so much time to run things. Okay, so you have jobs that would be run after hours. And these relational databases actually predate the internet. Remember that the first version of Ethernet is in the 70s, right? Right? First version of Ethernet is the 70s. We're not even talking about internet, right? Internet didn't become a popular thing until the mid-90s, where it became widely available. So we've got databases, relational databases are much older than that. So we've had to kind of adapt, and there's a lot of things that have shifted. Make sense? Okay. So that's a lot of history. Let's kind of take a break here because we're sitting at 2 o'clock. So let's take a 15-minute break, come back at 2:17. Upstairs. Grab that.
But I don't have my pet download on anything. Yeah, that bigger thing today. I'm playing on Minecraft. Your dog's cracked. We played at the end of the summer, dude. He like kicked everybody's ass. Fair, man. Demon fighter. You play on camera? They do it, but not a whole lot. My main games right now are Street Fighter, Good Gear, and Blaze 2.
I don't know. I'm kind of Sonic on. I don't know if you said
Something Sonic, he be excellent. One day I might be kind of sort of almost supposed to do that. But he's kind of a god. And he's what, like 21? I don't know. No. Like, this is like this is Mr. Federal all his life.
Go Smash?
I play a little bit Smash. But the Switch is officially my little brother.
Gotcha. I was like watching Mango and stuff like that, but Smash. Ludwig. You know who Ludwig is, bro?
Yeah, you know that name? Oh, that name?
Yeah. I don't know Ludwig, bro.
Why do you bring up the CFI role play?
You know that. So you do know that. You just, I mean, you have to know that. I just never played GTA. He had 2 million subscribers, though. He's not a nobody. You didn't want anybody, just one person.
Yeah, that's what it's saying. Taking it, learn, you feel that the best precise.
You want to say anything, Josh?
Yeah.
They must be anyway. Like what?
Yeah.
Yeah.
No,
This
this
is where the podcast.
I went there and they said my soul.
You don't even know that long, dude. You don't even know it. Oh my gosh. No, there's that.
No.
Where's the
Yeah, why did you find so much side project?
I thought you just, just like, I don't know.
Everyone knows I'm gonna listen to their computers. I'm like, I got another one of these.
Like the Walmart thing? I heard bad things.
It was fun to me. I listened to Jerry Seinfeld. I forgot the name. What was it? Where? The one.
Yeah, there ain't no way you were.
It was the one like I worked with Nancy when I was in high school. The stop format. And there was like, it's always the name, like, their palette down. Lady named Maureen. She was so hard to deal with. We found out that if you flirted with her, she would get your stuff down like right away. So we'd always go in and be like, oh, Maureen, you look real nice today. And she'd be like, oh, thank you, and like get her stuff down like, right away. It was awful.
That's the service experience.
You want to talk about your life before?
With an Olive Garden. So it wasn't so no, those were the actually first reserve jobs. Before that, I was a quick trip. 2 years I was on overnights. That was actually my original plan, was working at quick trip my whole life. And the couch before that. Couch was blast. Yeah, they're fire. Like, so good. With the cheese?
Yeah, it's like,
So the buffalo chicken rollers, you get a hot dog on them, put ranch on it. Oh, it's so good. You just spread the ranch on the bun, you put the buffalo roll on there. Oh yeah, it's good.
don't talk about quick trip
Those fries, I would never get those a lot.
that Rooster Fish one?
Yeah. Rooster Booster sucks, actually.
That's why I started, but like, slush is not good.
I used to like Monster, but not so much anymore. Does anybody even still get the original green Monster?
Yeah, is it the white one? That's what my wife is. She's like,
The original grill. You know that they still have like the most rows too, or like they did for the longest time. Like they still have like 8 rows. Yeah.
Oh.
The original monsters.
It's alright. I would do it.
Yeah, but like who's the
smell that makes it great.
You saw the full white cakes? You say like what's their signs or whatever? Which one you say like?
White rice.
Oh yeah, the white one. I think I drink that stuff.
I didn't really good. Oh, it's like it takes me back to like the middle of cornfields, just like hurling my guts out.
Did not have that personal experience of being honest.
I grew up in like a really small town, so just like party out in the field. That was like a party.
Never had you get that out trash cans.
Right.
But I mean, all black is not that great. So.
I like that.
Yeah, basically.
It's smooth.
And that Tito stuff is so smooth. I grew up in the kitchen. Almost puked on some girl boyfriend.
Nice. I I'll do shots. I don't know.
It's like when you go to the bar and
Hey, there's nothing wrong with Vegas. Bomb
it's so
Jolly Rancher or
order,
something,
man.
you know?
It's like these like Irish car bombs, like anything else. Like it's just like I'm so sick of like Vegas bombs and Jaeger bombs.
I'm gonna say even on the big day.
No,
Yes.
oh,
You seem like such an innocent kid.
I was just putting out one of the you tell the best.
Hey.
What's that? Yeah, we went to Illinois in the summer. It was stupid. It was stupid. Yeah, it was. It was so expensive. But it was like, it's more like the experience. I've been one in Colorado, but I've been one in Illinois. I'll go in there and see like what's like. Taxes were ridiculous.
If they just bump down the tax, people would buy a little off and they're gonna end up making more money anyways.
I think if Missouri does that, they don't well, also the business. People don't like Missouri, but you don't have people going to Missouri, but from Missouri to Illinois.
I'm surprised. I bet some Illinois people come here and know how much
It's close, yeah. Like you said, it's like St. Louis or something, sure. But don't you just go see the doctor and say go back? Yeah, you can.
Actually, there's medical stats from everywhere. There's one on the left side.
You work for these jobs since we're going to the
Have you worked at McDonald's your whole life?
We've been bagging on him for a job, like,
I'm just
last 2 days. He's like, he's not just like, we not talking about McDonald's.
I worked at a factory.
Yeah, I only work at factories. That's right. But I just, you said the old imagination.
Yeah, they were so miserable on like that.
When I first got
Yeah, I got thrown to get kidnapped all the time. Like this, like yeah, you don't. I was like, guy going here, 30 I mean, like, he grabbed his arm, two in his arm, bro. Like, I mean, we're gonna look down at this other way. I was like, alright, chill it, yo. No, you're right. He walked out the door.
Oh.
I was like, there's nothing I'm gonna do about this, I'm gonna be honest.
Yeah.
This man's strong enough to pick up 430 packs. Be my guess, there is nothing I can do there. But yeah. That was about all I saw. I only worked on South Limerick, so it was like crazy setting. But there was some. John Limerick, it's like South County area. South Limerick's a long road.
Yeah, I used to live with my grandma for a little bit. She lived right by, you know where the Melville High School is?
Yes.
I used to live on that area.
Yeah, my friend lived in Melville.
Melville? I didn't go to Melville, I spent some time with my grandma. She lived right next to high school. So I lived there for a little bit.
You said you lived in Switzerland then, right?
Yeah, was it 6.5 years there?
What was that like?
Very different.
Don't
Suffice to say, very different.
Do you remember any of it? Like, how young were you when you were there?
Yeah, I mean, we're talking about we moved there when I was 4 and moved back when I was 11.
I'm surprised you still even remember any German, like you said.
Ja, mein Deutsch ist nicht so gut.
Not very good.
But I've got a little bit of it still.
Is it true all they drink is carbonated water? Do you know any of that?
No, we don't drink carbonated water.
No, I was saying that. Well, one German teacher said that that's a lot of what they drink over there is mostly carbonated water. It's like they just get it in bottles. I was curious if there's any truth to that or not.
Have you gone back since you, like, as an adult?
I haven't as an adult. I need to, but I haven't gone back as an adult. I'd say it's, you've got your water, you've got your beer, you've got your wine.
This are like a lot of their beers warm too over there, right? But I heard that, they should do it now.
I think that's a regional thing. A lot of people who come to the States, one of the things they notice, and this is not just Europeans, but we use a lot of ice, more than the rest of the world does in our drinks.
Hey, blame it on the retail industry. They're the ones who don't give you the full soda.
Yeah.
That's their fault.
So I mean, they don't mind grabbing something out of the fridge and whatnot, but they're not going to add a bunch of cubes of ice to it. They're just going to take that. So it's not necessarily, that.
Are serving sizes a lot bigger? Like when you put it in beer, put something there?
I don't know where currencies stand now, but historically, I mean, prices have been higher in Switzerland than the U.S., but I don't know where those things stand right now. But remember, I haven't been back there in 20 years. I haven't been back there in 20 years, so it's hard to know what prices look like now.
So recently I found out that a daughter board is not spelled like dot or
okay.
It's DAW or like the relationship, your
okay.
daughter. All this time I thought it was a dot or
What are we?
D-O-T-T.
Yeah, no, but what are we talking about? I'm not
just
sure.
in general, someone spelled it out fine. I saw it spelled for the first time in my life.
Okay.
And it was just a shock, a culture shock.
That may be a little bit of a. There's different versions of German, basically. So the version that I'm most familiar is Swiss German, not High German, which is what they speak in Germany, in the majority of Germany. And so daughter is Tochter, as I'm familiar with a T. Not with a D at the beginning.
So you say you speak the Low German?
Not Low German, Swiss German.
Oh, so
it's different. Yeah. So Swiss German is a very different dialect, and maybe a little bit closer to Dutch and French than German in some ways, but it's really a very local dialect. There's even dialects within Germany itself, but Swiss German is a very different dialect entirely.
I kind of recently taken interest in these different languages. I just watched YouTube videos.
Yeah.
I think it's pretty interesting. Like to me, Low German seems easier to understand than High German.
Yeah.
It's a little more similar.
Yeah, I think Low German covers some areas of Germany, if I remember right, and it's not. Swiss German's neither of those.
If you know High German, right?
Actually, most people have a hard time going across that border. A lot of people do have difficulty even there, but at least the way that Switzerland runs, generally speaking, your Swiss German is what you talk, but if you're doing formal legal arrangements or stuff, or you have the politicians, they speak High German. That's kind of the language of government kind of thing is High German. Or it's very weird because you speak in Swiss German, but you write in High German. Although there's no written form of Swiss German. Really. I mean, you can, and people do, but it's technically not usually how people write. So coming back to this, so basically what I'm trying to get to is just kind of explain what the environment of relational databases is, right? And so there's some limitations. There's some things that they were designed for that maybe are a little bit different than what things look like today. And so you kind of need to understand that, and you need to understand that that means that things like, hey, I want to make a change to the database is an expensive thing, and you should really consider about and consider about doing that. Does that make sense? There's a lot of process that you want to do. You want to get your database right before you even start writing your code. Does that make sense? So it's very important to kind of sketch that out. You know, we're going to talk about ERD diagrams. It's really important to make a diagram of it and decide about the schema before you start writing any code. Because otherwise, you come back later and you have to rewrite a bunch of code, you have to change the database, and that's a huge pain in the butt, right? So we want to get that right. You know, we want to recognize that there's a cost to making mistakes there. And so that's kind of things we have to be aware of. So let's talk about some of the terminology when we're working with relational databases. First up is the schema. Okay, so the schema is the collection of SQL statements that define the structure and the constraints of a database. Okay, that's what a schema is. I'll repeat that. The schema is the collection of SQL statements that define both the structure and the constraints of the database. Okay, defines both parts of it. Okay, and so you can think of the schema as a really long SQL script that generates your entire structure. And you can write it that way. Okay, and say here's the script to create the structure. I can also write some SQL statements in there to add data in there, but in order to define a database, you basically have to write this giant schema even before you can put any data into it. Does that make sense? You can't put any data into a database in a relational database without having a schema first that defines those rules. Does that make sense? So like we defined that this table, this employees table, has a last name column, first name, last name, email, and age column. I've defined the names of those tables. Names of those columns. I defined the order of those columns. I defined, you know, what kind of data can go into them, right? So I've defined all of those things. A database then is an actual kind of implementation of that schema, right? It's this collection of tables and views and indexes that make up the actual data and has the data inside of it, okay? And so the database is represented by a collection of files on hard disks somewhere, okay? So that's your database. So you've got a schema which defines the structure, and the database is the thing that actually contains the data, okay? If you're thinking it from an OO perspective, you could say like the class is kind of like the schema and the object is like the database, okay? We then talk about tables. Tables are a collection of rows. There's also the thing that kind of defines what columns are there and that kind of things. Every column that you have in a table has to have a name, a data type. It can have constraints. It can also have an optional default value. So, for instance, if I don't say that, if I don't provide a value to that column, then it will use the default value instead. Does that make sense? And typically, if I don't set a default value, it will choose null as the default value. But I can do things like say, hey, this setting should be true by default. So the default value is 1. Or if I want it to be turned off by default, I would say the default value is 0. Or if I want to say by default, users are unapproved, so the default value would be unapproved. So all of that is part of defining the columns. Okay, so when you're defining a column, you have to define its name, its data type, its constraints, and its default value. Okay? At a minimum, you have to define the name and the data type. Okay? You can get away with just defining the name and the data type, but you're typically going to define all 4 of those things for a lot of cases. Default value, I say, is the least used one of that. There are relatively few cases where you're defining default value, because most of the time null is the right one that you want. You just want to say, hey, it doesn't have a value, so it's null. We also talk about rows. So row is a single data point, single entry in the database. You can think of it as really, when we're dealing with this in our programs, we think of those as actually the objects. Each row is an object. You also hear it called an entity. An entity is a more generic term when we're talking about objects within the database. So like if I talk about a document within a document database, it's still an entity. If I talk about a node in a graph database or an edge in a graph database, those nodes and edges could still be considered entities, right? So entity is a thing. And then you've got cells in the relational world, an intersection. You've got a single cell, which is a row and a column where those meet. That's where you store a single scalar value. So in relational databases terms, a cell or a field, we call it by either of those two names, a cell or a field, can only store a single scalar value. Okay, and that constraint is really important. Okay, a cell can only store a scalar value. What is a scalar? Anybody know what a scalar is?
All I can think of is mathematics.
Okay, which you're right, it means the same thing in mathematics. What does it mean in mathematics?
Does it mean it's like a numerical value?
Sort of.
In mathematics, there were vectors, and they were made up of scalars in
Right.
direction.
Or you have matrices, which are, you can either view a matrix as a group of scalars, or you can group it, say it's a group of vectors, right? So a scalar is a single value. So if you've ever taken Calc 3, you're familiar with scalars and vectors, and so a scalar is a single thing, right? So if you're talking about numbers, that's just one number. Scalar in this term can also be a string. A string is also considered a scalar. It only has one value. So that means in terms of storing a column, I can have my user have one first name. I can't have my user have two first names. Does that make sense? He can have one and one only first name. He can't have a collection of first names. And that becomes a problem as soon as you try to do things like this. So let's say I've got a blog. And my blog, I've got a bunch of blog posts on there. And every post has a title. It has a body. And it has some tags. Okay? Tags are a way to kind of be able to organize my posts. And so you can find everything that has those tags. You can think of, like on Twitter, you put hashtags at the end, and you get the same kind of idea. So my title is a string. My body is a string. What data type is my text? It's a string array. Okay. So now this title and the body, they're strings, they're scalar values as far as we're concerned. Yes, they're composed of basically an array of characters, but we still consider them as scalar values. But the tags is not scalar. It's an array of strings. So relational databases in general are largely unable to deal with this. There's been some recent changes where some relational databases can deal with this, but in general they cannot. I can't make a table like that.
And that's because earlier we said that in the cell in a relational database it has a single value.
It has a single value.
And that goes against an array.
Yeah, it goes against an array because an array is an array of values, right? So I might have my blog post have 3 tags, but where do I put that? Well, because I can only store one value, right? And so this is hard to deal with in relational database terms. There are some solutions, some workarounds, but this is hard. Does that make sense? And that's something you have to be aware of. So one of the things I'm going to ask you to do is design a database today, right? And that means you have to pay attention to this, is you can't create any tables that have arrays inside of them. They have to all be scalars. Does that make sense? It's a big constraint. It's a really big constraint. You have to make everything fit into that. Okay? And sometimes that means you have to add more tables. Another way I could try to solve this is if I'm okay with having up to 3 tags, I could say, well, tag 1, tag 2, tag 3. Now they're all strings, right? But I can't have more than 3 tags. And I'm going to make my SQL very, very complicated if I do that. Does that make sense? So you can do that. That's one way to do it, but we usually end up adding another table. Okay? But that's one of the constraints you have to work with. We also talk about relations and relationships. Interesting thing about relations and relationships, unlike a lot of these other terms, they don't necessarily exist in a relational database itself. We use the relational database to model relationships, but we may or may not store those relationships. Does that make sense? They're more of a theoretical thing. Okay, even though it's part of that name, even though the idea of a relational database is a combination of tables and relationships, we don't really have relations in the schema sense. Does that make sense? So it's more of a theoretical thing. And so that's one of the reasons that we're going to use these diagrams, is to be able to see what those relationships are. Okay? And so when we're defining these relationships, part of what we use is this idea of primary keys and foreign keys. A primary key is a unique identifier for a row within a table. Okay? Primary key is a unique identifier for a row within a table. Every table in the relational database sense should have a primary key. There are cases where you're allowed to have that optionally, but you really shouldn't do that. You should always have a primary key on every table that you have. Okay? And sometimes you can make that primary key be from some of the columns that you already have. More often than not, we have to add an arbitrary column, an extra column, to represent that primary key. And in general, we usually call that the ID. So every entity, every row is generally going to have an ID column that uniquely identifies it. Okay? It's kind of the easiest solution around. You just say, oh, we'll just add an ID column, and now we can uniquely refer to that row. Okay? And easiest way to do that is you say, well, it starts at 1. First record I add is 1, and then 2, and then 3, and then 4, and then 5. Right? So I have the ID just go, it be a number, and it automatically goes up by 1 every step. That's kind of the simplest version of it. There's a whole lot of security problems with doing that, and a whole lot of performance problems with doing that. But that's the easiest way to implement it. Okay? So primary keys generally just, in simple terms, it's just a number that uniquely identifies the row. We then have the idea of a foreign key. A foreign key is an identifier in another table that refers generally back to a primary key in the first table. Okay? So there's this, one of my students, I think, referred to it at one point as like the remote and the home and away from home kind of idea, right? So your primary key is when you're in your table that it belongs to, and foreign key, you're kind of using somebody else's primary key because you're away on a trip. Okay? So, or out of the country. So that's the idea. Foreign key is a number or a value that refers to another record. Okay, and that's how we create the relationships in a relational database. Is we use these foreign keys. Does that make sense? That's how we model the relationship. So when I'm creating a foreign key, it's kind of like this relationship where I say that this row belongs to this other row. It's like a child of it. Okay, because it creates kind of a complex relationship, but it's not symmetrical, if that makes sense. It's not the same from from the parent to the child, right? One is the primary. One is the one that that one's that's got the primary key is the parent, and then you have the one that's got the foreign key, and that's kind of its children. And in order for the children to be there, well, the parent has to be there first. Okay, so there's some relationships there. Okay, so that's kind of the terminology that we use when we're talking about relational databases. We use a lot of that terminology, fields and entities, specifically when we're talking about other kinds of databases, but it's a little bit different, okay? Because we're not talking about tables when we're dealing with other kinds of databases. So one of the tools that we want to get into now is talking about database diagrams. So as I've said, it's really important to make a model and plan your database ahead of time before you actually start writing code, okay? And so database diagrams are an easy way to do that. They don't require a lot of effort. You can usually make them in under 4 hours. And then you kind of have a blueprint for what you're going to do for the next 3 months, right? That's kind of the way this works out, is you say, okay, I'm going to sit down in 2 to 4 hours. I'm going to hammer out this diagram that's going to decide how I'm going to do my entire project, and then that entire project might take you a few months to complete. Does that make sense? A few hours of planning for several months of work. Okay? So they're a valuable tool, so you make sure you kind of make those decisions ahead of time. So an ERD is a tool for discussing the entities and the relationships in your database with customers, with stakeholders, and with developers. It's a way that actually most business people understand ERDs. They understand these database diagrams. They can look at it and kind of understand what you're doing because oftentimes they're actually taught that. So you can communicate on this level because it's not a very technical diagram. It's not meant to be. It's meant to be able to be at a level where you can communicate with business people that aren't programmers, that aren't developers, okay? And it's also just a way for all of you in the team to agree on what you're going to do, right? So maybe you have a team of 5 to 20 developers. You can come up with this entity relationship diagram, and now you know what you're going to build and how the schema is going to look and how the database is going to look. Make sense? And so it's really easy and cheap to update this diagram if we later change our minds, okay? Whereas actually changing the code is pretty hard, okay? So the point of this diagram is to work out some of the kinks in your design before you actually start writing the code. Before you start building the application, you create the diagram to decide on how are you going to store the data and what data do you need to store. Does that make sense? Okay, and I really recommend, regardless of what database system you're using to make the application, it's always worth taking a little bit of time to make a diagram. It's always worth a little bit of time to design and plan out what you're going to do rather than just jumping into the code. Okay, so there's a bunch of tools available to make these diagrams. Okay, you can make them honestly with pencil and paper. Okay, they're just squares and lines and circles and diamonds. Like, you can totally make them with paper, and some people you still can't, right? I don't generally make these on paper. I don't know that I've ever really made these on paper outside of a classroom setting, but you can. Okay, Google Docs. You can use Google Docs to create them. There's a bunch of other resources out there. You can use Umlet to create them, which is a UML diagramming software. Umletino is an online version of that. There's SQL DBM, database diagram, Lucidchart. There's a whole bunch of services that you can use to create these diagrams. I believe even Visio can create these as well. I would not recommend using things like Photoshop for this. They're not really designed to work well. You can use them. I wouldn't recommend that for this kind of problem, okay? As far as things are concerned, I only want to take these in Umlet this semester, okay? I'm going to have everybody do this in Umlet this semester. There's a bunch of other tools available out there. This is the one that I'm using, and that's the one I'm going to ask you to use. Cool? It's a pretty easy interface, and we'll talk about how to do that. I'm going to show you a video in a minute, and we'll get that installed. So that's what I'm going to ask you to make your diagrams in today, is to make them in Moonlit, as well as there's going to be another lab in a week or two where you're going to make one of these yourself on your own. Okay? So let's talk about how these ERD diagrams work. Kind of in the name, there's two parts to an entity relationship diagram. There's an entities and there are relationships. Okay? So the entities are the things, and the relationships are kind of the connections between those things. Now, depending on the situation, you might find that the relationships over time turn into entities as well. That's entirely possible, and you can do that. But generally speaking, you've got this division between things and relationships, things and connections. So if we're talking about an academics standpoint, you might say, well, we've got, if I'm trying to model this course, I could say I've got, or a school, I've got courses, and course is an entity, a student is a thing, a teacher is a thing, and I've got a user, right? I might have these different things, these entities. Does that make sense so far? The entities you have are really going to vary from application to application to application, right? So you have to figure out, first of all, when you're designing a diagram, you want to come up with the entities first. Before you do anything else, you just draw a box and say, this is the name of the thing, right? And I would even do this before you figure out any of the attributes or the relationships. So you just write out all of those. Okay. So now I know, I get through that and I say, at the end of the day, you usually end up having a good number of entities. So maybe at the end of this, I might even end up with 10 entities. That's not unusual. Next thing I want to do is I want to draw relationships between those entities. So for instance, if I've got students and teachers and courses, there are relationships between those, okay? So I can say that a student studies or is part of a course. Does that make sense? Okay? Or a teacher teaches a course, right? Notice that there's no direct connection, though, between the student and the teacher, right? The only connection to them is through the course. They're not meeting each other outside of the classroom. The only time they see each other is when they're in the classroom. Does that make sense? So that's their only connection. There's no direct connection between those. And that's not unusual. You'll find oftentimes there's things that don't have relationships between them. But you do want to capture all of the relationships that exist. Okay? One of those areas, remember from the reading, is duplication is something you need to consider, right? And it's very easy for duplication to get in if you have too many relationships, right? Where one relationship disagrees with another relationship. So there's a balance of having the right number of relationships. Not too many, not too few, but the right relationships, okay? And so you'll see the entities are represented by these square blocks, and I've represented the relationships by these diamonds, okay? I will go ahead and say that there are a lot of different flavors of ERD. Not everybody creates their ERDs the same way. And so just recognize that if you're looking at somebody's ERD, you may have to ask, does this represent an entity? Does this represent a relationship? What do these shapes represent? Because there's not a standardized language really for ERDs. I've seen it taught a bunch of different ways. Okay? So this is the kind of flavor that I'm showing you, but it's not always the same one that everybody uses because there's no standard ERD. Okay? But they have the same components, we just use different symbols. Yeah, this one's pretty standardized. We've kind of agreed on this part. When we're talking about the relationships, there's also this idea of the cardinality or the multiplicity. It goes by both names, cardinality or the multiplicity. Cardinality says how many things are on both sides of the relationship, okay? How are these two things related? Yes, there's a connection, but how many things are on both sides, okay? So when I'm looking at this, this annotation here with a hash on both ends says that it's a one-to-one relationship. one of these things exists exactly with one other thing here. So you might think if you have a division between like the users and their public profiles, every user has one public profile, every public profile corresponds to one user. That would be sort of a one-to-one relationship. Make sense? Only one thing on each side, and can only ever be one thing. One-to-many says on one side there's one thing that is connected to a bunch of other things on the other side. Or going the other direction, this one thing over here is connected to one thing on that way. One of the things you have to do is defining these relationships is you actually have to look at it both ways, from A to B and B to A, and determine what that relationship is, okay? And then finally, the last classification that we get is many to many. So you can cite this kind of sort of branching says that on one side there's many, and this side says there's one. So there can be one-to-one, one-to-many, or many-to-many. Make sense? Many-to-one is just the reverse of this, right? And so you see that sometimes come up, but it's basically, it's just another way of looking at a one-to-many relationship. Okay, so when we look at these relationships and we start looking at teachers, right? I can say a teacher can be teaching multiple courses, right? Teacher can be teaching multiple courses. So I start from here going this direction, and I'm going to say, okay, teacher can teach multiple courses. So I'm in this direction, I'm defining that relationship, that cardinality here. Going the other way, when I go from course to teacher, how many teachers can be teaching a course? One, just one. Just one, okay? I could technically have this be 2 or 3, but let's keep it simple and let's just say it's 1, okay? So every teacher, every course has one teacher, but every teacher can have multiple courses. And so you see there's a direction to that relationship. And one of the biggest mistakes that students make when they're creating these diagrams is they get the relationship wrong. Is you take the relationship and you put it in the wrong direction. If you get the direction wrong, your whole database won't work. Like that is, in terms of the decisions that you make in drawing your diagrams, the cardinality is the most important decision you can make. Tracking with me? Cardinality of the relationship will have the biggest impact of all of your decisions. So these little lines, 2 lines here, 1 line there, are the most important ones on the diagram. Okay? Make sure you include them. Make sure you don't leave them out. Okay? Because if you leave them out, you haven't done a good majority of the work. Okay? And I recommend figuring all this out before you get down and talk about columns and attributes, because it's a lot easier to fix these problems here than when you get down to having columns, and it's a lot more messy. Okay? Okay. So let's talk about this other relationship. So if I have a course, how many students can my course have? Well, not just one, right? That wouldn't really be a course, that'd be a tutoring session. So a course has many students. How many courses can a student have? Well, many, right? So the student can be part of multiple courses, which is this symbol here. And the course can have many students, which is the symbol over here. It gets a little bit confusing because it's the opposite of what you expect, right? When you're drawing the line, it's on the opposite side. Okay? Does that make sense? So we've got what kind of relationship between students and courses? And what kind of relationship do I have between teachers and courses? What was that? One to many? What's the relationship between course and teacher? Many to one, right? It flips if you look at it in the reverse direction. Okay? So this is the most important part. In fact, if you get this part right, that's actually enough to start writing code. If you have that, you can start writing code. Because that's the part that is really needed to get everybody on the same page. Does that make sense? The other parts, they're extra. They're things that we want to do, but they're not the most important thing. Okay? A lot of people get into these diagrams, and the first thing they do is they get in and define the columns and the attributes, and they say what data types do they have, and then later they come back and the last thing they do is define the relationships. You need to define the relationships first. Does that make sense? Okay, so let's talk about attributes. So in terms of designing attributes, we kind of add them in addition, we attach them to entities. So here we've got a student entity, and then around it are its many attributes. Okay? And so here, the student has an ID attribute, they have a given name, they have a family name, they have an email address, and they have date of birth. Does that make sense? And so remember, when we're talking about fields, we're talking about cells. Cells need to have how many values? How many values can a cell have? 1, right? So it needs to be scalar. So I need to make sure that all of these things here that are single valued, they can't be arrays, they can't be lists, they can't be objects. They just need to be a single thing. So like I wouldn't say the student has a name because a name has many parts. Okay? I wouldn't say they have an address because an address has many parts. Does that make sense? If you have something that has multiple parts, it's an entity in and of itself. Does that make sense? So like an address could be a bunch of attributes, or it could be an address entity. Okay? It's not just one single thing. On the flip side, I think somebody asked about dates. Okay? A date, can you generally break it apart and have meaning without the date as a whole? I would say generally not, right? If I break a date up and say, here's the hours and the minutes, the year, the month, and the day, I could break those up as attributes and treat them as numbers. But more often than not, when I'm dealing with dates and times, I'm going to represent that as a scalar value, just so we're clear. Okay? Dates and times are generally represented as a scalar value. Cool? Not as objects. Even though in the language that we work with, even though when we get to programming, we usually treat them as objects. Dates and times are generally objects once we get to programming with them. But in the database terminology, they're a single value. Make sense? They're considered a scalar. Okay, so let's talk about how we define these relationships. So remember, as I said, in order to define a relationship, you need a primary key and you need a foreign key. Okay? So every entity that you create needs to have a primary key. Okay? Some cases they're optional, but generally speaking, it should be there. Okay? All of your tables, all of your entities should have a primary key of some sort. Okay? So for instance, the course, I might call that the course ID. Okay? Course has a course ID that uniquely identifies the course. Okay? And there's two kind of conventions for naming that. You can either call it the ID, or you can call it like this, the course ID. So I could just say ID here is the name of it, or I could say course ID. I've seen both. Either of those are acceptable. Okay? So you either take the name of the entity and add a ID at the end, or you can just call it ID. Either of those is okay, as far as I'm concerned. There are some requirements for that primary key. Okay, so that primary key has to satisfy these requirements. It has to be fixed. It cannot be updated later. Okay, it has to be fixed. It's something that can't change. So for instance, if I'm talking about employees, I generally can't use the last name as a primary key. Why? Is it fixed? It could change. In fact, a lot of people, when they get married, they change their last name. So I can't use that as a primary key because it's going to change at some point. Okay, so it has to be something that's unchanging. We can't edit it later. It has to be unique. I can't have multiple copies of that same primary key within table. Same thing happens with last name. Multiple people might have the same last name. We both have the last name of Smith, right? So that would work as a primary key, because you'd have multiple records with the same value. Does that make sense? So it has to be fixed, it has to be unique, and it also can't be null. Okay? The primary key is not allowed to have null values. Make sense? If you want an acronym for that, call it FUN. Fixed, unique, and not null. Make sense? Those things have to be true for your primary key. Okay, if that's not true, then it doesn't work as a primary key. And so oftentimes we find ourselves creating arbitrary binary keys, just adding something in there, an arbitrary number, because there's nothing in the real world to uniquely identify it. Does that make sense within the data? Okay, next topic. So the other side of things is we have foreign keys, okay? So the foreign key is part of implementing that relationship. So here we've got teachers and courses. We decided that a teacher can teach many courses, but every course belongs to, is only taught by one teacher. So here the teacher has a teacher ID, right? That's their unique identifier. That's their primary key. The course has a course ID. That's its primary key. But we need to link those two together. So over here I add a teacher ID. And this teacher ID field says that this course is being taught by that teacher. Does that make sense? Or I can call this, taught by, you can call it whatever you want, right? I could call it, that call. But that's what creates this relationship. If I don't have this foreign key over here, then there is no relationship. Does that make sense? The other thing that it does, okay, anytime you add a foreign key, this creates a one-to-many relationship. Okay. By the virtue of the teacher ID being over here, I'm now saying this course can't be taught by multiple teachers. It's not possible because every course only has one teacher ID because it's a scalar value, right? So this inherently limits that there, but it does allow me to have the teacher to have multiple courses, right? Because the foreign key's over there, it's not here. If I flip this and I say, let's put a course ID over here. Well, now I'm saying that the teacher can only ever teach one course. They can teach one course and then they're done. You have to let them go. Maybe we can hire them again and then we'll have a new teacher ID. But I have to let them go if I put the course ID over here. Does that make sense? Because they would only ever be part of that. So remember what I said. It's really important to get your cardinalities right. Because if you get your cardinalities wrong, you end up with the foreign key on the wrong side. Does that make sense? And if you start getting four keys on the wrong side, then you have a lot of work done. Cool? One thing you don't want to do, never put a foreign key on both sides. That's the worst case scenario. That's a database that is basically broken. Because if I put a course ID over here as well, and a teacher ID, I actually can never add any teachers or courses to the database. Because by the foreign key being here, I can't add a course until the teacher exists. If I put a course ID over here, then I can't add the teacher until the course exists. So I can never add a teacher or course because there's never any teachers or courses. Right? So it's really important that the foreign key is only on one side of the relationship, not both. Does that make sense?
So this design right here really doesn't allow you to make a course unless there's a teacher.
Correct.
The moment you're
Correct.
a course.
Yep, I can't create a course until there's a teacher. Now, what I could do is I could allow nulls on this here. And so I say, let's say you create a course with null for the teacher ID, and then later create the teacher and update the teacher ID. Does that make sense? But I can't say, okay, this is for teacher 5. Teacher 5 doesn't exist yet. I'll create it tomorrow. I can't do that. I can say there's no teacher, but I can't say that there's this teacher in the future. Does that make sense? The foreign key actually limits. The foreign key is a constraint. It says that this other thing has to exist before you can create it. There's another gotcha with foreign keys. Okay? This course, right, has a reference to a teacher, right? I can no longer delete this teacher. Because if I delete the teacher, I have to take all of his courses with him. They're gone, right? Because all of the courses depend on the teacher being in existence.
Same with the students, right?
Same with, well, the students, yeah, if I need to delete, I can't delete a teacher because the courses and the students would need to potentially go with it. Yeah, I can't delete the course because all the students would go goodbye.
But that's all right, because when do they delete things out of data?
What was that again?
But that's all right, right? Because when were they going to delete that stuff out of data?
Things happen. Things happen. You know, sometimes you need to, what if you need to, something happens and something happens to the teacher, it now needs to be taught by another teacher. Well, I can create another teacher and change the teacher and point to the new teacher, but then I've also now forgotten who the original teacher was. Yeah, I know what the current teacher is, but I don't know what the original teacher was anymore, because I can only store one value. Cool? Okay.
Can you substitute it out?
What do you
use like a new teacher for the older teacher?
Yeah, I could put in a new teacher ID. So I can say right now this is taught by teacher 5, and later I can change this to be taught by teacher 7. But it can never be taught by both teacher 5 and 7. Make sense? Okay. So in terms of this, as I said, they create a one-to-many relationship. They're implemented as fields, which refer back to the primary key of another entity. And they constrain the value of that field. This field is now constrained to the valid teacher IDs. So again, if there's no teacher 7, I can't have a teacher 7 over here. And again, so that you're always going to put them on the many side of the relationship. So that's a really important thing to get right. If you have any question when you're making the diagram about your thing and you're not sure that it's right, call me over, ask me if the one and many side is right, because that's the easiest thing to mess up, right? Is the direction of your relationships. Now, one of the things that happen here, notice that inherently this creates a one-to-many relationship, okay? I can use this to create a one-to-one, that's possible, but that doesn't actually allow for a many-to-many relationship. You see that? This doesn't allow for many-to-many relationships. So in reality, relational databases only really let you have one-to-many relationships. That's all you get. So everything has to be defined in terms of one-to-many relationships. Does that make sense? So if I want to define a many-to-many relationship, I have to use kind of a weird trick. And the weird trick that we use for many-to-many relationships is we use something called a bridge table. We use a bridge table to stand in the middle. Okay? So in the middle here, I have a course and I have a student. Remember, previously these are a many-to-many relationship. I can't do that. So I put a table in here. I call it a bridge table called the course student table. And this tracks what students are in each course. Okay? I can add more columns to it. I can add more attributes, more fields if I need to. But at minimum, it needs to have a course ID and a student ID. So this record says, okay, this course and student ID pair, they're together. They have a relationship. Does that make sense? So this is actually an entity that represents a relationship. Remember how I said the diamond, I think on this, that diamond is sometimes an entity, it's sometimes not. If you start to need to add data to that relationship, or if you need to have that be a many-to-many relationship, it starts becoming an actual thing. Does that make sense? So this bridge table is really, really important. Now, how does this work? So look at the relationships. The course has many course students. The student has many course students. So I'm only using many-to-many relationships. There's actually no many-to-many. I'm only using one-to-many relationships on both sides. There's no many-to-many there. So if you're drawing the diagram and you find out you need a many-to-many relationship, cut it out, you have to replace it with this. Does that make sense? Because there's no way in a relational database to do this other than using a bridge table. Got it? No other way around it. Do you have a hand on it?
No,
Okay.
it sounded, that's all.
So you'll notice here that I've got two foreign keys. So I've got a course ID and I've got a course student. These are both foreign keys. Oftentimes I find myself also needing to add a primary key because neither of these can be the primary key. Neither of these is unique within the table. So I might have a course student ID in here as well. Right? I might have a third ID. I could call it ID or I could call it course student ID that's uniquely defined in this row. Does that make sense? That's one of those tricks you really have to write down. If you haven't yet, take a note of that in bridge tables and take a note of the diagram, because you're going to really need to refer to this as you're doing the exercise. There's a few places where you'll need to add bridge tables in order to make it work. So that's kind of the whole of the ERD shtick that you need to understand, right? Is you've got entities, you've got attributes or fields, and you've got relationships and cardinalities. That's kind of the whole, right? So it's not a huge, complicated thing to learn. It's just it takes some practice to get it right. Okay? Now, what I generally use to diagram my ERDs is I use UML instead. UML stands for Unified Modeling Language, and it's a much more standardized sort of language. We've agreed on what the symbols mean. And because we've agreed on what the symbols mean, we can now use tools that use that unified language, okay? So in UML, it looks a little bit different, okay? When I'm creating these diagrams in UML, I've got these boxes that represent entities or tables. So I've got a course table, I've got a course student table, and I've got a students table. And so you see the name, traditionally these are name of an object. So I've got the courses, and I've noted this with the elements you see at the top. I'm saying this is a table, this is a table, this is a table. So that top header tells you what it is. And then within there, I've got some notation that says, what are the attributes? Okay, so like my courses has a course ID, and it has a course name. My students have a course student ID, which is the primary key. My course ID is student ID, maybe a grade. And then they have students have a student ID given name and family. And so that's kind of how you define the attributes using UML, right? So rather than a bunch of little circles, which gets really hard to draw pretty fast, I'm writing it this way. Does that make sense? So slightly different syntax. You'll notice here I've got PK standing for primary key. I've got FK here as well, standing for foreign key. Everybody see that? And so it's a little bit backwards because at least feels a little bit backwards what you're used to coding, because it's the name and then the type, name and the type, instead of what you're used to writing in like C#, it's type and then name. Okay? And so there's a colon between those.
So does these numbers right here, like 1 and 20, does that mean
Yep.
20 students can be in like one course?
Exactly. That's actually what's happening. So we're saying this number over here says that the course can have up to 20 students. It's going to have at least one student, but it's up to 20. And this course student only belongs to one course. Okay. Vice versa, this student can be up to from one course up to 5 courses, but this record only corresponds to one student. Every record in here is only corresponds to one course and one student. It's one pair of those two. Does that make sense? So that's what this is adding a little bit more bounds on what those relationships can be. And that's often helpful. It's often helpful to know not just infinitely large. Sometimes you can actually put really low limits on and say, well, realistically, I could be part of 20 courses, but it's probably going to be 1 to 5 courses. I could have a course with 200 students in it, but I'm only going to build a system that's big enough for 20 students in it. Okay, so that can be helpful to know the bounds of your cardinalities. Okay, I'm still putting in the crow's feet here. So this is the many side here. That's the many side here. Make sense? Okay. So let me show you the tool that I use to make this diagram. So this is the tool that I use to make it. It's called Oomlet. You can download it from, I believe, oomlet.com. But before we get into it too much, I'm going to just play the video here. That'll give you kind of an introduction to the UI, and then we'll install it in a minute. Okay? If I can turn the audio on. Am I plugged in? No, audio's over there. There we go. That cable up here. Oh. I need to run that into there's my headphone jack.
And just like before, we modified the relation in the property panel. This makes it very easy, for example, to change the direction of a relation or to change its type.
That was something.
You can also edit all the elements you see in the
There we go.
palette above. This way, you can set up and use your own element templates that you might have to use more frequently.
Okay. So here's the introduction to this tool.
Hi, this is a brief introduction to our open source tool, Oomlet. It lets you draw UML sketches really fast, just like on a sheet of paper. Today, I'm going to show you 3 main features. First, let's see how to create a simple class diagram. We just add a class element to the main panel, and then we can modify it in the property panel to the right. So let's change the name and then add member variables and some methods. Of course, you can use copy and paste, which makes this very efficient. As you see, there is no pop-up dialogues and no mouse dragging involved.
So as you can see, you kind of got your palette up here. These are things you can add to your diagram. But it's not in your diagram yet. So you take things in here. Anytime you double click something in there, it'll add it over here to your diagram. And then when you select it, you've got the property panel down here where you can just write some text and modify it. So for instance, you can see the top line here is the name of the object. And then you've got a dash dash, which creates a horizontal line. They've got some properties here, dash dash to create another line, and then they've got some methods. Does that make sense? It's pretty fast, it's pretty easy. That's kind of the starting point there.
Same thing for relations. Let's just add one to the diagram first. And just like before, we modified the relation in the property panel. This makes it very easy, for example, to change the direction of a relation or to change its type. You can also edit all the elements you see in the palette above. This way, you can set up and use your own element templates that you might have to use more frequently. The second main feature are complex diagram types. Let's have a look at activity diagrams first. Here we change the name and add some activities.
I'm going to stop that there because they've already covered really the part that we need to see, right? So this part before it is kind of conventionally known in UML as a class diagram because you can kind of see they're representing classes and such in there, but it works perfectly fine for doing database diagrams as well. Cool? Questions? Okay, so what I want you to do now, we're all going to go install this piece of software. So I want you to go out to oomlet.com. So oomlet.com, if you scroll down, there's a screenshot. Here's actually the video that we just watched. If you want to watch it again, you can go there. You're going to hit download up here in bold. Okay, so that's going to take you to the download page. We want to talk the newest version, which is 14.3 standalone. So you're going to click and download that. So you can grab 14.3 standalone. Once it downloads, you'll see down here that it's a zip file, right? It's a zip file. It's not an installer. Okay, so we need to put it wherever we want it to be. And for me, I typically just put that on the desktop. That's usually where I end up putting it. So I'm going to go to here, show in folder, and kind of see it there. If I look at it, it's got a folder in there. So I'm going to right click and I'm going to say extract all. Okay, it's going to tell me to create this 14.3 standalone folder. I'm going to go ahead and create that. It's just going to be in the downloads folder for a minute. And so you can see that I've got on here, I've got in my downloads, I've got a folder named 14.3 and I've got oomlet there. So we can take this folder, move it to my desktop, close that. So now I've got oomlet on my desktop. Okay. Now if you dig into there inside of the 14.3 folder, you'll find an oomlet folder. And you see that there's this oomlet.exe. Everybody see that? That's the program that we want to open up. So we're going to open up oomlet.exe, and it'll look like this. Told you need to go to Java. So yeah, you may need to go to java.com as they're suggesting and go ahead and update your Java. I'll give everybody a moment to get caught up here. Just go ahead and hit extract. And it's on your desktop already. Yeah. So well, okay, so .exe won't work because that's a Windows thing. Yeah, it's .js. You probably install Java first. So really Java. Yeah. You actually get the Java runtime. So hopefully with that in place. Okay. So installing Java. The future one is plug into Dawn. Okay. So what you need is you need to install the driver. So without the drivers, it's not that used to. So you're just using that. You're just using that. I may have a way around it. Okay. So this is the tool we're going to use to create these diagrams. It's called Umlet. You kind of saw how to use it. You had a quick tutorial on that. And so we kind of saw how you add classes. You kind of double click from the palette, bring it in. You can add fields by typing in. You can also add relationships and cardinalities. And then finally, we can talk about export PNG. So what I'm going to do real quick is create a very simple diagram. And we can kind of see how this works. So I'm going to double click on simple class up here. That's going to add it up. And I can kind of drag it around. So let's say we're doing, this is my customer. So I'm going to name that customer, ... And maybe in here they have an ID, they have a name, and they have an email. So this is kind of a really quick sketch. ID, name, and email. Okay. I'm going to actually double click on customer. That's going to make me another copy. And so this is going to be my order. And so my order has an ID and maybe a date. Okay. And we'll just start there. Or maybe I'll call it the order date. Okay. So I've got a starting point for that. I want to add a relationship, so I'm going to pick one of these arrows. It actually doesn't matter which arrow you pick with to start with, because we're going to change what it looks like. So I'm going to double click on the arrow. It's going to pop over here. I'm going to hook one side here to one side there. Okay? Kind of line these things up. Okay? So with this relationship, I can change this. If you look at the bottom right panel, you'll see there's this LT equals. That stands for line terminator. Okay? That's what LT stands for. It's line terminator. So what I want to do is change the terminator there. If I go back to just a dash just looks like a line. Okay? So if it's LT equals dash, it's just a line. Okay? What's the relationship between orders and customers? One to many. Okay? So a customer can have how many orders? As many as they want. But every order only gets shipped to one customer. Okay? So when I write this in, if I do greater than or equal to, it's going to look like this, greater than and then a dash. Or if I do dash and then less than, it's going to look like that. So depending on how you type in the line terminator, will change the order of that. So this is dash less than is what I did. Okay. If you want to add labels to that, which is what you saw in my example, you're going to add another attribute. I'm going to say M1. M1 is 1. M2 is 0 ... star. And so that little bit will let you add all the cardinality stuff to it.
Can't quite see that text.
So this is LT is equal to dash less than. M1 is equal to 1. M2 is equal to 0 ... star. So LT, M1, and M2. That's it. M1 and M2 just give you a label on either side of the relationship.
Okay. Thank you.
That's it. So everybody kind of understand what we're doing here? You kind of understand how to write that in there? One of the things that I did earlier when I showed you the example is I did some stuff with Guillemets. So for instance, if I wanted to have a primary key, I wrote that like this. It's actually really easy. It's just less than PK, greater than. It turns those into the Guillemets one that shows up in the diagram. So that's all you have to do. Pretty simple. Okay, so that's kind of the start of doing that. One of the things you want to do is once you get done with the diagram, you're going to hit save. And so maybe I'm going to save that to my desktop, and I'm going to show that my order example. You're going to see what extension this is saving it as. See, it's saving it as a UXF file. Okay, so that UXF file is specifically to Oomlet. You can't open it up anything else. But that gives you the opportunity to edit it later. So you want to keep that original source file as a UXF file. And then when you get to the point where you want to export it, what you're going to do, let me show you one thing here. So I'm going to I'm going to go up here. I'm going to say export as. I'm going to export this as a PNG. Okay. I'm going to save that as order example to my desktop. Okay. Now there's one weird behavior that always trips me up and always trips people up working with this tool. Let me bring this over. And let's look at the file that I just exported. Okay, so if I open up that file, is there anything wrong with the exported picture?
It's only the customer.
Yeah, it's only the customer.
So because you had to click?
Because I had that selected. So the way that Oomlet works is if you have part of the diagram selected, it only exports that one part of the diagram. If you don't select anything, so if I just click out here, see nothing's in blue, when I go export this diagram, it's going to look a little bit different. So export as PNG, save it again, overwrite it, yes, and there's my whole diagram. So just be careful if you're exporting it to make sure you select everything. Cool? Now, what I want you to turn in for me today is going to be that UXF file, right? Is that original source file. So what I want you to do is we're going to go to the last bit here. So one of the videos that you watched kind of gave you this process, the process of going through and making a database, okay? The kind of steps that they gave you, the instructions that he gave you, are first thing you should do is determine what the purpose of the database is and write that out. You know, determine what is this database meant to do, what data is it meant to capture, write that out. That's step one, right? So you know what your goals are. I'm going to give you your goals today so you won't have to write that out yourself. The next question is to figure out what all the bits of data are that you need to collect, whether they be entities, whether they be relationships, whether they be attributes. Then it's a matter of kind of dividing it into entities, dividing it into tables, figuring out what goes where. You start writing out all the tables and you put all the things together. I honestly usually start by just laying out entities and then start adding relationships, and then finally I'll add attributes is how I usually do it. In there, once you've got that in there, you kind of identify the primary and foreign keys. So every table should have a primary key identified with PK. Anytime you got a relationship, you need to figure out what the cardinality is and what the direction of that relationship is. So on the many side, that's where we're going to add the foreign key. Okay. Anytime you find that you have a many-to-many relationship, remember we're talking about bridge tables. You need to add a bridge table to fix that relationship because we can't have a many-to-many relationship. Only be one-to-many. And so also then make sure that there's foreign keys on the many side of every relationship, every one-to-many relationship. We're going to mark that with an FK, and you refine your design as you're kind of working towards getting it to the place where it makes sense and it has the data that it needs to have and all the relationships are in the right direction. Okay? So that's kind of the process. And that's what I want you to follow through and do here. So here's the group exercise for today. We've got about an hour left. So that's kind of the time you have to work with right now, unless anybody wants to stick around longer. I want to ask you to break up in groups of 2 and just pair up, either with just the person you're sitting next to or with somebody else in the class. And I want you guys to kind of work together to create one of these diagrams. And part of that is just getting a feedback cycle of working with somebody else to see the kind of things that we talked about today, right? To make sure your relationships are in the right place and that kind of experience. So I want to ask you to group up in groups of 2. I'm going to ask you to create an ERE using Oomlet, as we just saw. And you're going to design the database that's going to store this information. You want to design the information for courses, namely for a school, right? So it's going to include this information. You need to be able to store in students, teachers, courses, assignments, and grades. And don't forget to include all the relationships between those things. Okay. I'm not looking for necessarily all of the attributes, but it's really important that you get the relationships right. Okay?